last speaker for the structural glass session. Laura Galuppi, Dr. Laura Galuppi, she's an assistant professor in the University of Parma, and she has developed a very innovative analytical method that she calls BAM, right? From an old theorem of Betti's theorem. She's going to explain all about it. But it's a way that you can see differences in the pressure of the IGUs. So we'll be talking a lot about her model and the validation of it. The floor is yours.
Okay, thank you for your kind presentation. Okay. And good afternoon to you all. This work I'm going to present is being developed at the University of Parma, Italy, in collaboration with Maffei Engineering. And it is with a new and innovative calculation method for insulating glass units. Now, as it is well known, insulating glass units are composed of two or more glass plies that are connected along their perimeters by means of edge spacer bonded with structural edge seal. And the resulting cavities are filled up air or gas just to improve the thermal and acoustic insulation properties of the unit. There are two different in kind type of loads whose the IGU can be subjected. So the first type is represented by changes of the internal pressure of the gas that may be due to either a change of altitude, of barometric pressure, or temperature. And these are usually denoted to as climatic loads. This change of pressure results, so it is equivalent to a distributed load acting on both glass panes. The second kind of loads is represented by the external loads that may be either uniform, line distributed, or concentrated, that are applied on one of the external panes. And the loaded pane can share a portion of the applied loads with the other panes through a complex interaction mechanism between the deflection of the glass plates and the variation of the cavity volume and of the gas pressure. This mechanism is usually denoted to as load-sharing mechanism, and both literature and standards prescribe different methods to evaluate the load sharing. So probably the simplest one is the method proposed by the AES-TM, according to which each glass panes composing the IGU carries a portion of the applied load that is proportional to its flexural inertia, so to the cube of its thickness. It may be verified that this is equivalent to completely neglect the compressibility of the gas. On the other hand, the method proposed by the European norm 16612 accounts for the gas compressibility through the definition of an insulating unit factor. However, both of these methods can be used only for climatic loads, so change in barometric pressure and temperature, and for uniformly distributed loads. A more refined method is that proposed by Feldmayer that allows to consider also the cases of line-distributed and concentrated load. This is a very accurate method, but however it is quite cumbersome because it requires the calculation of the volume enclosed between the deformed shape of the loaded pane and its initial, so the flat configuration. And this calculation should be done for each load case, so as a function of the load position and so on. More recently, a simpler method called the Betti's analytical method, or BAM, BAM, I don't know, has been proposed, and it is going to be included in the final version of the Eurocode on structural glass. This is a very general method because it can be used to evaluate the load sharing for IGUs arbitrarily constrained at the borders, so for any kind of boundary condition, more or less any kind, and for arbitrarily distributed load. Furthermore, it can account for IGUs of arbitrary shape and composed of an arbitrary number of glass plates. Just to discuss more in detail the load sharing mechanism, let me consider, this does not work, okay? let me consider the case of a double glazing unit, so composed by two glass plates, subjected to an external load applied on the lower pane. Let me call it plate 1. In this case, obviously, the load provokes the deflection of the loaded pane, and this produces a variation of the cavity volume, and consequently, a change in the pressure inside the cavity. The arising of the pressure inside the cavity is equivalent to a load producing the deflection of the not loaded plate 2, but also decreasing the deflection of plate 1. So now, from the point of view of the analytical treatment of this kind of problem, the deflection of the two panes is simply governed by the plate theory, so for example, by the Kirchhoff-Love plate theory. On the other hand, the cavity volume may be evaluated as the integral over the plate area of the difference between the deflection of the two plates. And finally, the volume variation and the pressure variation are related by the ideal gas law. Let me remark that while the deflection of the upper plate of plate 2 is quite simple to be determined, since it is simply the deflection of a simply supported plate under uniform load, the deflection of the loaded plate is strongly affected by the external load, so by its position and so on. And this is much more complicated to be determined. So the question is there a simple method to evaluate the integral over the plate area of the plate deflection? And what can be of help is a classical theorem in linear elasticity that is due to the Italian eminent scientist Enrico Betti, and the so-called Betti reciprocal theorem that is considered a linear elastic structure, and that is subjected to two different equilibrated set of forces. Let me call them system A and system B. The theorem states that the work done by the load state A through the displacement produced by the set B is equal to the work done by the set B through the displacement of the set produced by the set A. So if we consider, for example, a simply supported plate, here it is represented as a beam, but it is a plate, subjected to a concentrated load, for example, and as a system B, the same plate under a uniformly distributed load, the Betti's theorem allows us to evaluate the integral over the plate area of the displacement in system A just as a function of the quantity delta, so of the deflection of the plate under a uniformly distributed load, measured at that point where the load is applied. And this is a remarkable result because it allows to evaluate the integral of the deflection due to a concentrated load without studying the deflection of the plate under a concentrated load. Furthermore, the deflection in system B is very simple to be evaluated because, as I said, it is simply the deflection of a simply supported plate under uniform load, and the solution is recorded in books. And this deflection may be written as a function of a non-dimensional shape function, phi, that only depends on the panel shape, as well as on the plate stiffness and area. So, passing to an IGU and try to apply the Betti theorem to an IGU, let me consider as a system A the actual load system acting on the IGU, so the external loads and the pressure change delta P. And as a system B, a fictitious pressure inside the cavity. So we need to evaluate the reciprocal work, and an important point is that the work done by the system B through the displacement of the system A is simply related to the volume variation. So it can be evaluated without studying the deflection in system A, and so it does not depend on the external boundary condition of our IGU. Furthermore, the deflection in system B are again very simple to be determined and may be written again as a function of a shape function. Okay, now we need to evaluate the work done by the load system A through the displacement of system B, and this is quite simple because we need essentially to determine these two terms. The term in green, that is the volume variation in system B, may be simply written as a function of a non-dimensional coefficient phi A, that is the mean value of the shape function over the plate area, and obviously depends on the stiffness of the two plates and on their area. The term in red instead takes different expression dependently on the kind of the applied load. So in case of an uniformly distributed load, it depends again on this coefficient phi A, while for a line distributed load, it depends on the mean value of the shape function over the line where the load is applied. And again, this is a non-dimensional coefficient phi L. Finally, for the case of an IGU under a concentrated load, it depends on the value of the shape function at the point where the load is applied. So, thanks to this simplification, we can write the Betti's reciprocal theorem in a very simple way. And from this equation, we get a very simple expression for the pressure change, that is for the load sharing, where delta P simply depends on non-dimensional coefficient depending on the geometry. Here, P0 and V0 are the initial pressure and volume of the cavity. So it takes very simple expression, and remarkably, analogous expression may be obtained also for the case of line distributed and concentrated load. So the BAM method requires to know only the coefficient phi L, phi A, and phi P, and provides very ready-to-use formula that can cover all the cases of loading condition. These coefficients are provided in the literature in form of tables or graphs. For example, for the case of rectangular plate, this graph shows the coefficient phi A simply as a function of the aspect ratio of the plate. This second graph provides phi L, again as a function of the aspect ratio, that here is made to vary between 0.2 to 5, so to account for both the cases where the load is applied on a line parallel to the short or to the long edge. And in this graph, the different curves correspond to different position of the applied load. And this is the analog graph for the case of plate under concentrated load, so to evaluate the coefficient phi P. Literature also provides the similar charts and tables for other shapes, as for example for triangular shape, but in the most general case, they may be evaluated by means of finite element analysis. Let me present now some results. Results are here. Okay. Here we consider the case of a rectangular plate under different kind of loadings, and the results are obtained by means of the Betti's analytical method, are compared with the results obtained by means of the software MIPLA-ISO. Results are here presented in terms of the maximum deflection of the not loaded plate, that is obviously proportional to the pressure variation in the cavity. This first graph shows, as a function of the aspect ratio of the plate, the maximum deflection of the not loaded plate for different values of the glass thickness. The continuous line represents the results of the analytical method, while the triangles are the numerical results. This graph on the left refers to the case of a pane of an IGU with area of 4 square meters, and the one on the right to a plate with an area of 9 square meters. There is a very good agreement between analytical and numerical results, and it may be verified that the maximum error is of the order of 0.5%. Now, for the case of an IGU under a line distributed load, here these two graphs consider square plates with the variable position of the load. The graph on the left refers to a plate with the area of 4 square meters, and that on the right to 9 square meters. Here the loading position is made to vary, and again we get a very accurate results. To investigate also the influence of the aspect ratio of the pane, here it is made to vary between 0.25 to 4, and this graph considers the case where the load is applied at the midspan. Now, these graphs consider instead the case of a square double glazing unit under concentrated load. These are perfectly analogous to what I showed in the previous slide. And this last one, consider the variation of the aspect ratio. In all these considered cases, the maximum error is of less than 0.7%. So we have an excellent agreement between the analytical and the numerical results. Now, as I said at the beginning of my talk, this method can be applied to IGUs composed by an arbitrary number of glass plates. So the analytical treatment is completely analog to that I presented before, but for example, for the case of triple insulating glass units, we need to evaluate the two different pressure changes in the two different cavities. They turn out to be dependent on non-dimensional coefficients that takes expression slightly more complicated than the one I showed before, but however, they may be simply implemented in an Excel file. They are quite simple. And once we get these coefficients, the formulas to evaluate the pressure changes are very simple. It has to be noticed that the coefficient phi L, phi A, and phi P appearing in this equation are exactly the same for the double glazing units. So they do not depend on the number of glass plies. Just some comparison also for the case of TGUs. Again, I consider rectangular plates. Here, the case of uniformly distributed load. In this graph, the deflection of the two not loaded plates, so of the intermediate plate and of the other external plate, are plotted. Again, there is a very good agreement between analytical and numerical results. For the case of line distributed load, here this graph shows the deflection of the external not loaded plate as a function of the loading position, alpha, so of that quantity. And the different curves correspond to different aspect ratio of the IGU. The graph on the right instead considers only the case of load applied at the midspan and investigates the influence of the plate aspect ratio. And these are more or less the same graph for the case of TGU under concentrated load. So the graph on the left considers different position of the load, while that on the right investigates the influence of the aspect ratio. In all the comparison that we performed, the maximum error is of less than 0.7%. So there is, again, an excellent agreement. So, in conclusion, this Betti's analytical method provides formulas that are very easy to be implemented and allowing to evaluate the load sharing, so the pressure change in the different cavities of IGUs. It can also be applied to the case of IGU under climatic loads. Here I have not presented the results for reasons of time, but accurate comparisons are recorded in different papers. And the strength of this method is that it does not require to solve the problem of the plate under the concentrated or line concentrated load, but it only requires the knowledge of the coefficient phi A, phi P, and phi L. And it can be used for IGUs composed by an arbitrary number of plates. It can cover all the cases of loading condition, and the comparison with the result obtained by using MIPLA ISO, I've confirmed that it has a very good accuracy. So here there is a short reference list of paper dealing with this kind of model, and I thank you for your attention.